Okay, our last topic in this unit is on related rates. Now, related rates, these are dealing with variables changing at different rates or different speeds. Now, recall that dy dx is really telling us the rate that y changes with respect to x. So keep in mind that derivatives are really rates of change. So this is going to be an application to that. So we have some steps here which we'll go through as we jump into this first example. So here's the example. How fast is the area of a square increasing at the instant when the sides are 4 feet long if we know the sides increase at a rate of 1.5 feet per minute? So the first thing we want to do back up here in step 1 is to try to draw a picture and label the quantities that vary. So I have my square, okay, and let's suppose we call each side S, okay. Now it says in the problem that the sides are increasing at a rate of 1.5 feet per minute. So the second step is to identify these rates that are known and the rate of change that is to be found. So the way we say that the sides are going to increase at a rate of 1.5 feet per minute is we say ds dt equals 1.5 feet per minute. So you're used to seeing dy dx. Well, ds dt, this is the rate at which the sides are changing. Now, because my 1.5 is a positive number, that's implying that it's increasing. If the problem said that it was decreasing at a rate of 1.5, I would make that negative. So ds dt is the rate at which the sides are increasing with respect to time. So I don't have a dx on the bottom, it's a dt, again t for time. So with all of these related rates questions, understand that it is now to be done with respect to time, okay? Because think of it as a real life situation. So we're trying to find how fast is the area of the square increasing. So we're going to get in the habit of writing out what it is we're trying to find. So we're trying to find dA dt. Capital A stands for area. So that's the area at which the square is increasing with respect to time. So imagine the square getting bigger and bigger and bigger, okay, starting off really small and then increasing in size. We're trying to find how fast the area is increasing at the instant when the sides are 4. Okay, so it's almost like we're going to pause the growth or the rate of change at the moment when they're 4 feet long. So the third step is to find an equation that relates these quantities. Well, what are the quantities we're talking about? Well, we're talking about the area and the side of a square. So you know that area would be side squared, right? That's the formula that relates our variables together in this problem. The next step is to differentiate both sides with respect to time, okay? And then solve for the derivative that will give the unknown. Well, we're trying to find dA dt, so that's what we'll be solving for. So the derivative of A, think of it as just going to be 1, all right? But with respect to time, so we're going to turn that into dA dt. Again, technically it's times 1. Think of this as when we were doing problems with implicit differentiation. If we had a y term, we tacked on a dy dx. Well, here for all of our variables, we're going to be just tacking on whatever that letter is. So you'll see as we go through. So now the derivative of s squared, use your normal rules for derivatives, just like we did with implicit differentiation. That would be 2s, but now my variable in this case is s. So I have to put ds dt, that's what I have to tack on to it. So this is all, notice my denominators here, this is all with respect to time, okay? So We've differentiated both sides, and now the last step is to evaluate at the appropriate point. Well, the appropriate point is the instant when the sides are 4 feet. So again, the sides are increasing at a rate of 1.5 feet per minute. So every minute that goes by, the sides in this square are growing by 1.5 feet. So at the instant when the sides are 4, we're trying to figure out what is the rate at which the area is increasing. So this is where we're just going to plug in now all of the pieces of information we know. So I'm trying to find dA dt equals to, well, s is going to be 4, and my ds dt we identified over here to be 1.5. Okay, so if we multiply that all together, you're going to get 12. Now, since this is area, it's not just going to be feet, but it's going to be feet squared per minute. So the area is increasing by 12 square feet every minute based on the fact that the sides are increasing by 1.5 feet per minute. Let's look at the next example. So, pebble dropped into a pond. We have ripples forming concentric circles. That's a circle within a circle. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When this radius is 4, at what rate is the total area of the disturbed water increasing? So you have this idea of concentric circles. Here is my radius. Okay. Again, look at the information in the problem, write down what's given, and write down what you're trying to find. So the radius r is increasing at a constant rate of 1 foot per second. So dr dt is equal to 1 foot per second. All right, and we're trying to find the total area, all right, at this particular moment when the radius is 4, we're trying to find the rate of the total area at which it's increasing. So we're trying to find, just like the last one, dA dt. So this time we have to come up with an equation to relate area of a circle with the radius r. So think about what that would be. If you're thinking area is equal to pi r squared, you're right. So now we're going to differentiate each side because we want to turn it into a rate. Remember, a derivative is really just a rate of change. So dA dt equals, now pi is just a number, so I can multiply that 2 down to it. And then I'd have that r really to the first power. And we're doing this all with respect to time, so I need to tack on a dr dt. So now we plug in, trying to find dA dt. We have 2 pi. The radius is 4. So notice we don't do anything with that number until the very end. All right, and I have 1 for my dr dt. Again, keyword increasing. If it were decreasing, we'd make it a negative. So you end up with 8 pi. That's a nice exact answer. All right, or if you were to make it a decimal, 25.1 square feet per second. That would be our answer. So that's how fast the area would be increasing in this pond, all right, at the moment when the radius is 4 feet. One more example. Now they just give us an equation, all right, with 3 variables in it. Okay, so we don't have to actually find the relationship. They give it to us. At a certain instant, when x equals 1 and y equals 3. So at this instant here, this is information we're going to hold off on using until later on. But we know that at this instant, x is decreasing at 2 units per second. So dx dt is equal to negative 2 units per second. Keyword here, decreasing. And y is increasing, so dy dt It's increasing at a rate of 2 units per second. How fast is z changing at this instant? So we want to find dz dt. So get in the habit again of writing down your givens and write down what it is we're trying to find. So they give us the formula relating these variables. So now we have to integrate both sides. Not integrate, differentiate. Integration, that'll be in a couple months. So the derivative of z, dz dt equals, over on this side, think about which rule we're going to need to use. Hopefully you're thinking product rule. So 4y cubed dy dt, because I just took the derivative of a y term, times that x cubed that comes along for the ride, plus, now we reverse what we just did. We have y to the 4th times 3x squared, and then don't confuse this with implicit differentiation. Yes, it's an x term, and with implicit differentiation, with the x terms, we just found the regular derivative and didn't tack on anything. But that's when it was with respect to x. This is with respect to time, or t. So we have to tack on dx dt. So we're trying to find this dz dt. So now it's a matter of plugging in. Now we're looking at the instant when x is 1 and y is 3. So 3 goes in for y. My dy dt we said is 2. X is 1. Sorry if you hear a Frozen playing in the background. The kids are watching that. And our dx dt is -2. Alright, so we clean all of this up, and we end up getting, this is 216, this ends up being minus 486, which is going to give us -270 units per second. And then the question goes on to say, is z increasing or decreasing? Well, it's going to be decreasing because of that negative. Okay, we will practice more in class. Goodbye.